Recorded.
Alright, hello, welcome back to another Mathcounts meeting. Today we're continuing 2015 Nationals from number 1 on target. So if 2015 squared minus x squared equals 5 times x plus 2015 and x is less than 0, what is the value of x? Alright, so we see that the left side is the difference of squares, so we can factor that, and that would be good because we have a x plus 2015 on the right side. So we can cancel x plus 2015 from both sides. Okay, so we can cancel it from both sides, and we can do that in the case where x does not equal negative 2015, right? Because then we'd be dividing with 0. Okay, so now we have 2015 minus x equals 5, and this says x equals 2020. Okay, now x has to be less than 0, so x equals 2020 is not a solution. So where's our problem here? Well, our problem was that we assumed x does not equal negative 2015, so now we should test x equals 2015, or sorry, x equals negative 2015, and if we plug it into here, we see that it works, right? Because we get 0 on this side and we get 0 on this side. So then our answer is x equals negative 2015. So, whoops. Okay, so the takeaway from this problem is that when you divide by factors, you have to be careful on when that factor equals 0. So the simplified expression that you get, it's only in the case where that factor will not equal 0. Anything you want to say, Bill?
Oh, I mean, you summed it up pretty well, so no. I think you summed it
Okay.
up very well.
Whoops. The radius of a cylindrical can is 5 inches and its height is 2 inches. The increase in volume when x inches are added to the radius of the can is the same as the increase in volume when x inches are added to its height. What is the value of x if x is greater than 0? Express your answer as a common fraction. Okay, so basically we have a cylinder, and one thing we do is we add x inches to the radius of the can, and the other thing that we do is we add x inches to its height. And in both cases, its volume increase is the same, and we want to find what x is. Well, we should set up an equation with this, and we know that its increase and volume are the same. Well, if its increase and volume are the same, and it increased from the same cylinder, that means its volume has to be the same, right? So then we can just make formulas of their volume, and we can set them equal to each other. So the volume of the x inches are added to the radius of the can is going to be pi times 5 plus x squared times the height squared, 2 inches squared, right? And then this is equal to pi times 5 squared. We're not changing anything to its radius, and we are increasing its height by, whoops, this should not be squared. It should just be times its height, yeah. Okay, and it's just going to be multiplied by 2 plus x, the new height. Okay, and now we just solve for x. So we can cancel out the pi's. We're going to get 2 times x squared plus 25, whoops. Okay, sure, we could just do that. Plus 25 plus 10x, and it equals 25 times 2 plus x. And then this simplifies to 2x squared plus 20x plus 50 equals 50 plus 25x. Okay, so we can see that the 50s cancel, and we just have 2x squared minus 5x equals 0, which is nice because we can factor out an x. We can factor out an x, and then we will get 2x minus 5 equals 0. Okay, and it says x has to be greater than 0, which means that we can't just have x equals 0 here. So this 2x minus 5 has to be 0. So then if 2x minus 5 is 0, then x just equals 5 halves. So our answer is x equals 5 halves, and oh yeah, there it is. Yeah, x equals 5 halves, and I forgot to check the answer for number 1, but yeah, it is negative 2015. All right. Okay, how many positive integers have the same number of digits when written in base 5 and in base 8? Okay, so what we can do is well we can look at say like 3 digits, right? We can look at the 3 digits number, or the 3-digit base 5 numbers and the 3-digit base 8 numbers, and see what range of values those take in base 10, right? And then we compare which of those numbers are equal in base 10, and that will be the number of numbers that satisfy our same number of digits thing here, right? Okay, so yeah, we'll just do that. So we're gonna start with 1 digit. So we'll look at 1 digit first, yeah. Okay, so in base 5, what numbers can you have that is 1 digit? Well, 1 through 4, right? And what is this in base 10? It's just 1 through 4 because we're multiplying this by 1, right? And in base 8, we can have 1 through 7 as the first digit, and this is just 1 through 7 in base 10. And yeah, this is pretty easy, I would think. And now we just compare these two ranges, right? How many numbers are in both of these ranges? Well, it's just 1 through 4, which is just 4 numbers. So we can add this to our total. We can make a list of our total, and we'll have 4 in here. All right, let's look at 2 digits. So 2 digits in base 5, we will have 1, 0 through 44, right? And in base 8, we will have 1, 0 through 77. Okay, now what are these in base 10? Well, this is just 5 through 24, and this is just 8 through 63. And we actually don't have to list out like these things anymore. We can just realize that like the 2-digit range of base 5 in base 10 is just going to be 5 to the first to 5 to the second minus 1, right? Like that. And this is the same thing with the 8. So we can just apply this every time. Okay, so now we look at the intersection of 5 through 24 and 8 through 63. So that's just going to be 8 through 24. Yeah, okay, so, and this is just going to be 24 minus 8 plus 1, the number of numbers in here, which is just 17. Yeah, okay. Now we look at 3 digits. So, right, we don't have to list out like the actual base numbers. We can just say it's 5 squared to 5 cubed minus 1. So it's just 25 to 124. And this is just 64 through what, 8 cubed. We have calculators, so 8 cubed is 512. So it's going to be 64 to 511. So this intersection range is going to be 64 to 124. And if you don't understand like why the 3-digit range would be like 5 squared to 5 cubed minus 1, you can just let us know and we can explain that. All right. So this range, intersection range, is going to be 124 to 64. So then this is just 61 numbers. So we'll add that to our total. Okay, now let's look at 4 digits. Okay, so that's just going to be 125 to 5 to the 4th minus 1, which is 624. And then this is going to be 512 to 8 to the 4th minus 1, which is 4095. Okay, we see that our range is 512 to 624. And the number of numbers in this range is just 113. Add that to our total. Okay, now 5 digits. We're gonna have 625 to 5 to the 4th minus 1. Whoops. Oh no, sorry, 5 to the 5th minus 1. and that is 3, 1, 2, 4. And then we're going to have 4096 all the way to 8 to the 5th minus 1, which is 32767. Okay, and we see that this range doesn't overlap anymore, right? Which means that base 5 and base 8 don't share any more like 5-digit numbers that are equal in base 10. And this is going to continue for all of our digits after this, right? Because the bottom of this base 8 range is going to increase more than the top of this base 5 range, right? Because every time for every digit we are multiplying this by 5, right? And we are multiplying this by 8. So this is going to get bigger and bigger, and this is going to be always smaller than that. So this is all of our total. So now we just add this up, and we get a total of 195 numbers. Yeah, so that's our answer. Anything you want to say, Bill?
I mean, this probably just have to think about, bases and like how they work, I guess. I mean, there's not much to say. You just have to find the ranges of each digits and then just find where they overlap.
Yeah. All right, let's move on. One corner of a square of side length 12 units is folded down to meet the midpoint of a side as shown. What is the area of the shaded trapezoid? Here, there we go. All right. Yeah, so we have a square. Its side length is 12 units, and it's folded. And this vertex touches the midpoint of this edge. And we want to find what the area of this shaded trapezoid is. Right, so how are you going to do this? So let me draw a rough figure of the diagram here. So it looks something like this. And our dot dot dots can just go like that. Okay. So how are we going to calculate the area of this trapezoid? We're gonna need to find its two bases, right? If we find its two bases, and we already know its height, then we can find the area of it, right? So our objective is to find this side and this side. Okay, so how are we going to do that though? Well, let's try to just find this side first, okay? So we know that this touches at the midpoint of the side, so we can go ahead and say that these sides are 6. And we also know that this side is 12, right? Okay, so we can set this side to x, right? And then we can use the Pythagorean theorem on this side, and this side would equal x squared plus 36, or root x squared plus 36, sorry. Okay, and we can see that if we unfold this this side back to here, it would line up with the x and join to form a 12, right? So then what can we say? We can say that x squared plus 36 plus x will equal 12. Okay, so how we solve for x here is we want to get the radical on one side, so then we can get rid of the radical by squaring both sides. So move the x to the side, square both sides, we'll get x squared plus 36 equals 144 minus 24x plus x squared. X squares cancel nicely, and then x will just be 144 minus 36 over 24, which is just 4.5, or 9 halves. I'll keep it as 9 halves for now. So x equals 9 halves. Okay, and we wanted this side, right? So let's go ahead and calculate that. So 9 halves squared plus 36 rooted. And then you get 7.5, and this is just 15 halves. So we just got this side. It's 15 halves. now our objective is to find the other side, the other parallel side, which is this side, right? Let's call this x now. Oh, let me erase those marks. Yeah. Okay. So we want to find this side, right? And we already have this side, so all we need to do is find this side. This is kind of hard, right? Because it's not really connected to much, right? We can try to like do the folding thing again by like folding it back out there, but that's kind of hard to do because we don't know what this side is, right? Okay. Um, so what should we do here? Well, one thing we can do is we can draw this connecting line here. And we know that this side is, or this angle is a right angle because it's one of the corners of the original square. And we know that these two angles are the same, right? And we know that this angle is a right angle because it's the corner of a square, right? So then what can we do? We can say that these two triangles are similar by AA. And that's really helpful, right? Because then we can connect our x side to something. So yeah. And also, um, uh, this is going to be the complement of this angle, right? Let me just have that as two of these angle marks. So if this is the complement of this angle, then this will be the same as this angle, right? Because this is a 90-degree angle and all these have to add up to 180, right? So then these are complements, but this is the complement of that. So these two angles have to be the same. And this is also a right angle. So these have to sum to 90. So those are complements. So this has to be that double angle as well, right? And so this has to be the double angle as well, right? Okay, so then we can see that this triangle is similar to this triangle, right? And that's good because we know the side lengths of this triangle. All right, so then what can we say? Let's label this side as y, and we can say that this side, 9/2, over this side, 6, will be equal to x over y, because we did the one on the one tick angle and then over the two tick angle, and that's the same thing here, right? All right, so then 9/2 over 6 is just 3 over 4. This equals x over y, so then y will equal 4/3 x. Okay, so then this is just 4/3 x. All right, and um, oh, okay, yeah. So we can apply the this is also this triangle is also similar to all these triangles, right? So and we know the side of this side right here. So with these ratios, we can get what this side is, right? And then once we have this side, we can figure out this side from Pythag, right? And we know that this side is 4/3 x, and if we connect these two sides, we'll have a full 12 side, right? So then we can use that to solve for x here, and that is what we want, right? Okay, so let's do that. So again, use the ratios. So 9/2 over 6 will be equal to this over that, right? Let's call this z for now. Okay, so this is going to be equal to 6 over z. So then this is 3/4, so 3/4 will be equal to 6 over c. C will be equal to 4/3 times 6, and that is just 8. Okay, so z equals 8. And then we can see here we have a 6, 8, 10 right triangle, right? Okay, and again, this 4/3 x side connects with this 10 side to form 12, right? So 4/3 x plus 10 will equal 12, so 4/3 x will equal 2. So x will equal 6 over 4, which is just 3/2. All right, cool. We found x and it's 3/2. Okay, So now we have both parallel sides, 3 halves and 15 halves, and we know the height or the length is just 12, right? So then the area of our trapezoid is just 1/2 times 15 halves plus 3 halves times the height, which is 12. So this will be 18 halves times 6, which is just 9 times 6, which is just 54. And we can see that as our answer. Okay. Send this back in. All right. Okay. The consecutive integers from 1 to n inclusive were written on a chalkboard. One of the integers was erased, and the mean of the remaining integers was 35 and 7/17. What integer was erased? Okay, let's just convert this into an improper fraction. So that as an improper fraction is 602/17. Okay, so what are we doing here? We have some integers, we're taking out one, and then the mean of all of those rest integers is 602/17. And how do you calculate mean, right? You calculate mean by summing all the numbers, and you put it over the number of numbers that you had, right? And if 17 is in our denominator, this means the number of numbers that we had have to have 17 as a factor, right? And the number of numbers that we have after erasing one number is going to be n minus 1, right? So then what can we say? We can say that n minus 1 has a factor of 17, or we can say that, n minus 1 is congruent to 0 mod 17. Okay, so now what can we do? Well, we can try n, or n minus 1, right? So the first value of n minus 1 we can try is 17, obviously, right? So then n would be equal to 18. So what we should do is we should see the sum of the numbers of 1 to n, which is 18 in this case. We should see if that is larger than 602. Because it has to be at least 602 for everything to work, right? So let's try that. The sum of the first n natural numbers is just going to be n times n plus 1 over 2, right? Okay, so if we do that, we get that the sum of 1 to 18 is 171. Now this is way too small, right? So we should try another value of n. So the next value of n minus 1 that we could try is 34, right? And then in that case, n would be equal to 35. Now we should see what the sum of 1 to 35 is, and that is 630. Now, this looks pretty good, right? It's greater than 602, so maybe this would work. Well, you have to be careful here, right? Because in this case, we have n minus 1 as 34, right? So we're going to be dividing by 34. But we don't want the denominator to be 34. We want it to be 17, right? So we're going to have to cancel out the 2 that is in 34, which means what? Which means our numerator has to be double as big as 602. So is 630 double as big as 602? It's not. So n equals 35 is not going to work either here. So now let's try the next step up, which is going to be n minus 1 equals 51, or n equals 52. So the sum of those n integers is going to be 1378. And this has to be at least as big as 602 times 3, which is 1806. So it's not big enough. So let's go to the next step up, which is 17 times 4 plus 1, which is 69. Okay, and the sum of the first 69 natural numbers is going to be 2415, and this has to be at least as big as 632 times 4. which is 2408. And you have calculators on target, right? So this is not bad. Okay, so it has to be at least as big as 2408, and we see that it is, right? Okay. So so what's happening here is that we have n minus 1 is 68, and this is 4 times 17. So we need to cancel it with 4 times 602, right? And so 4 times 602 has to be the sum of our numbers with 1 erased, right? And 4 times 602 is 2408, right? And if we don't erase any numbers, our sum is 2415, right? So then what number should we erase? We should erase the difference of these two numbers. So that is just 7. Yeah, okay. Yeah, let's look at the answer. Oh, whoops. Yeah, the answer is 7. All right, anything you want to say there, Bill?
Um, well, I mean, this problem is just like trial and error, I guess. You're just trying numbers. Uh, I guess there's not really much to say about this. Um, it's pretty straightforward. Yeah.
Okay. Let's move on to number 6. As Kyle walked along the street at constant speed, he noticed that every 12 minutes a bus passed him traveling in the same direction as Kyle, and every 4 minutes a bus passed him traveling in the opposite direction as Kyle. If all of the buses travel at constant speed and leave the terminals at each end of the street at equally spaced intervals, how many minutes long is that interval? Okay, so what's happening here is we have 2 train stations, and in each of them, the buses are leaving at equally spaced intervals. So maybe there's a bus here, and then there's a bus here, and then there's a bus here. Oh, okay, that's not very well drawn. Okay, that's like this. Or maybe, okay, maybe the bus should be smaller. Uh, I'll just draw the buses like this. Okay. So they're going to be at equally spaced intervals. So these buses are traveling this way. And then we also have the same thing at the other station. So these buses are traveling this way. And just consider them like mingling in over here, right? And then so we have Kyle, and he's walking in this direction. And when he sees these buses, he sees them coming to him at intervals of 4 minutes. And he sees these buses coming to him at intervals of 12 minutes. And we want to know how many minutes long is the original interval. Not that Kyle sees, but that I guess a not moving observer would see. Okay. Um so how should we do this? Well, um essentially what we have to utilize here is that when Kyle is moving in this direction, the net speed of, or yeah, the speed of like, or so let's say there's some distance between this bus and Kyle, right? And the net speed at this distance decreases will be the difference of Kyle's speed and the bus's speed, right? And in this one, the distance will be covered by a net speed of the bus speed plus Kyle's speed, right? Okay, so how do we use that? Well, let's think of this side first. Okay, so a bus is going to just pass Kyle, right? So this bus just passed him. Okay, so if this bus just passed him, after 12 minutes, this bus will pass him, right? Okay, so what does that mean? Um, this means, okay, so the net distance between Kyle and this bus, when this bus is at Kyle, is this distance, right? And we know that this distance will be covered by Kyle's speed minus the bus speed, or the bus speed minus Kyle's speed, right? Okay, so let's call the bus speed x, and let's call Kyle's speed y, and let's call the distance d for now. So this this distance between the bus and Kyle will be covered at a speed of x minus y. And we know that this takes 12 minutes, right? Because after he sees this bus, he will see this bus in 12 minutes, right? So 12 minutes times this net speed will give us the distance. And um and we can also apply to the same thing here, right? But it's going to be with 4 minutes, and it's going to be covered by speed of x plus y equals d. Okay. Um, and we know that the distances are the same, right? Because the buses are traveling at equally spaced intervals, and the buses have the same speed. Okay. And the problem doesn't state anything about like the distances of the buses. Like we can essentially have the distance of the buses to be whatever we want, right? Um like uh like if we have this distance as something, it will scale up the speed to be like in the same scale, and it won't affect the interval of time at all. But basically, like the problem doesn't say anything about the distance. So we can just say the distance is anything. Okay, so let's say the distance is 1 mile. Okay, so then we have some equations here. Then we have x plus y equals 1 mile over 4 minutes, right? And if we convert this into hours, it's just what, 60 minutes over 1 hour. So this is just 50 miles per hour. So x plus y is 50 miles per hour. Okay, and then x minus y will be equal to 5 miles per hour, right? Okay, now we can just sum these. Then we have 2x equals 20 miles an hour. So x equals 10 miles an hour, right? Okay, so x is the bus's speed, and we said the distance was 1 mile, right? So the bus is going at 10 miles an hour, and it's it's um it's spaced 1 mile between other buses. It will travel through that distance in 6 minutes, right? Which means that a new bus will appear every 6 minutes, right? Which means that our interval is just 6 minutes. And let's check our answer. Yeah, it's 6 minutes. Um, Anything you want to say about that, Bill?
Yeah. So for this problem, like what Austin did, he just set a distance, like, this, like, this is, it is a specified distance, and you're dealing with, so when I look at this problem, my thought was that, a problem like this, normally I've seen a problem like this where it gives you the speed of, it gives you the relative speed of the bus as it passes by, and if us is go in the same direction, opposite direction, you can take the mean. And so that's why, like, I thought of, like, you should you should give them a speed so you can calculate speed of it, like, the actual speed of it, and then you can do it backwards again, I guess. Yeah. Um, let's see. Um, you can also do this like this because speed is like speed is correlated, inversely proportional to time. You could have found the what was it called? What's it called? The reciprocal of the mean of the reciprocal of the two times. So the meaning of 1 over 12 and 1 over 4, that's 1 over 6, and the reciprocal of that would be 6. So you could have done it that way.
Okay. Um. Wait, yeah. Why does that work? The harmonic mean and the
Yeah, that's what it was called, harmonic mean. I was trying to remember what it was called and I forgot. The
uh.
harmonic mean.
Oh yeah.
I
Why
guess
does
it's
that
just
work?
because speed is going to be inversely correlated. Like in a given distance, and in this case, like a given interval, the speed, like the interval is like constant. So speed is going to be inversely proportional to time. So you could just find the harmonic mean of this, and that would avoid like having to set a thing.
Okay. Sure. Um.
I mean, what you're doing here is basically finding the harmonic mean, but instead of doing like 1 over the number, you're doing 60 over the number, if you think about it.
Um. Do you want to explain that more? I don't know. Uh. Like you're saying speed is inversely proportional to the time.
Yeah,
But
in a
or
given,
how does that apply? How does that apply?
uh,
Uh,
well, you can,
aren't the buses speed the same anyway?
okay, I meant like relative speed.
Okay. Okay. So okay, then you can say, I mean, from that you can say like x plus y is three times three times as large as x minus y, right?
Yeah.
Okay. And then you can solve from there, right? But
Yeah.
how did you use the harmonic mean though?
The harmonic mean, I guess. mm, Well, like the mean of the thing, the mean of if you're given the relative speed of the bus going the same direction, opposite direction, you can just find the mean of that, right? Like you can find the mean of that to find the actual speed of the bus if you're given the speed of the bus, relative speed of the bus going the same direction and the opposite direction. So my logic was if you can do that and time is going to be inversely proportional to the speed, you can just basically do the inverse, like inverse proportional form of mean, I guess. I don't know how to exactly say it, which is going to be the harmonic mean.
Okay, sure. All right, let's move on. Okay, an unfair coin is weighted so that it lands on heads with a probability of p where p does not equal zero. The probability of getting three heads and one tail in any order in four tosses of this coin is the same probability as getting four heads. What is the value of p? Express your answer as a common fraction. All right, well, we can just make formulas of those two probabilities and equal them to each other. So the probability of getting three heads and one tail is going to be the number of ways you can arrange that times the probability of all of those, right? So how many ways can you arrange three heads and one tail? Just four, choose one, right? Which is just four. Okay, and then put the probabilities of the things, which is just p cubed, the three heads, and one tail is one minus p, right? Because the probability of a head and a tail have to add up to one, right? Okay. And this is equal to the probability of getting four heads, which is just p to the fourth. Okay. So we can cancel out a p cubed on both sides. With this case being p does not equal zero, but it tells us that p does not equal zero anyway, so this is really matter. Okay, so now we can solve for this. 4 minus 4p equals p. And then 5p equals 4, so p just equals 4/5. And yeah, that's your answer. So pretty easy problem, I would say. Okay, if x and y must be positive integers no greater than 100, how many ordered pairs x, y exist such that the least common multiple of x and y is 10 times the greatest common factor of x and y? Okay, we should think of how you calculate least common multiple and greatest common factor with this. So x and y, let's say they have some primes in them, right? So like 2 to the a, 2 to the not another 2 to the a, 3 to the b, and 5 to the c, right? And y is 2 to the d, 3 to the e, and 5 to the f. Okay. So what would be the greatest common factor of x and y? Well, we would look at each of these primes, and we would look at which one of these exponents is the smallest one, right? And we would use that as the exponent of our 2 in our greatest common factor of x and y, right? So, we can say this as 2 to the min of a comma d, right? And we can do this for all of the things like this. And we can extend this for more primes as well. I'm just gonna show it with these few. Okay. Okay, so how do we calculate the least common multiple of x and y? Well, in this case, we're gonna take the highest powers of these. So it's gonna be like the same thing as this, but with the max function. So 2 to the max of a comma d, 3 to the max of b comma e, and 5 to the max of c comma f. Okay, and then it tells us that the least common multiple of x and y is 10 times the greatest common factor of x and y, which is saying that the least common multiple of x and y over the greatest common factor of x and y equals 10, right? Now, what we can do is we can use our exponents here, right? We can use our exponents, and these are dividing with each other, to say that 2 to the max of a comma d minus the min of a comma d times 3 to the max of b comma e, and I'm not gonna write it all out because it's kind of long, but yeah, and this is going to equal 10, right? Okay, so now what is that saying? Well, that's saying that the max of a comma d minus the min of a comma d has to equal 1. And the same thing with the 5. The max of c comma f minus the min of c comma f has to equal 1 as well. And all the other primes, max of all the other prime exponents minus the min of the prime exponents has to equal 0, right? So that this just equals 10. Okay, now how do we apply that? Well, the max and the min of like these exponents is always going to be like one or the other, right? Like if a is the max here, then d has to be the min here. If d is the max here, then a has to be the min here. Okay. So if the difference of these is 1, that's just saying that the difference of a and d have to be 1. And so the difference of our two exponents have to be 1, and the same with 5. And all of our other primes have to have a difference of exponents of 0, which means what? Which means that they have the same amount of all other primes in their prime factorization. Okay, so um, what I did here was more of like a proofy way to do it. But I mean, you can just think of this yourself in your head and think of it pretty fast on the test. You definitely don't need to go through all of this. You can just think of um, like GCF is grabbing the lowest exponent of these, and least common multiple is grabbing the highest exponent of these. So if the least common multiple is 10 times as much, then our difference of twos and fives has to be one, and the others have to have no difference. So yeah. Okay, now let's use this. So um, so we should do a little bit of casework. So yeah, okay. Without loss, okay. So no, let's assume x to be the biggest one, and we're just gonna multiply that by 2. So it doesn't say x is the biggest one. So this is just gonna be symmetrical if we say x is the biggest one. So we can just multiply that by 2, right? Okay, so say x is greater than or equal to y. Okay. So then with these we're gonna have two cases, right? One where x has a and c one larger than d and f, y's d and f. And we also have the case where x's c is one larger than y's f, but x's a is one smaller than y's d, right? Okay, and so what is happening in those cases? Well, in the first case, these are just one larger than um, y's things, right? So that just means x is 10 larger than y, right? So in that case, x is 10 times y. And in the other case, this was one larger, but this was one smaller, right? So then x would equal 5 halves y. Okay, and what are these? How many cases do we have this with integers, right? Well, we're going to have x equals the set of 10, 20. It has to be multiples of 10, right? For y to be an integer, and we can go all the way to 100. So this would be 10 cases right here. And then these x has to be a multiple of 5 for y to be an integer, right? So x can be any multiple of 5 all the way up to 100. All right, and this is just going to be 20 cases. So we have a total of 30 cases where x is greater than or equal to y, and we said we had to multiply this by 2, right? So then our total number of cases is 60. And yeah, that's your answer. Okay. Anything you want to say here, Bill?
Um, I mean, like Austin said, this is you can definitely do this way faster. Like you do not have to like prove everything. You could just think of this problem in like in terms of, oh, what I need is for one of the for like when you take the least common multiple and the greatest common factor, you're gonna have like factors left over. You're gonna have like numbers left over, and then so we I mean something you can think is like basically I want there to be an extra 2 and 5 or an extra 10 in one of the numbers, and so you can think of it like that. And if you think of it like that, you can just think like you can also think if one of the numbers is a multiple of 10, if then if like I choose a multiple of 10, then the other number will already be defined. And then likewise for the 5, for 2 and 5, if you choose a number that's a multiple of 5, you've already defined the number that's a multiple of 2. So you can think of it that way, which will be, there's going to be 10 multiples of 10 and then 20 multiples of 5. So that's 30 and then times 2. So that's going to be 60.
Yeah. Yeah, you could have done that all in your head, like really quickly, actually. So yeah, on the test, definitely don't go through like all of this. Um, I just did this more of a proofy way. But if you're doing this on the test, it would definitely be better just to like think of it like that. Yeah, okay. So that was all of 2015 national target. Nothing too bad. Um, and now let's move on to 2015 national team. Um, okay, it's right there. All right. What is the least positive integer n such that 2 to the n plus 1 and 2 to the n minus 1 both are composite? Okay. Well, what you can do here is first just trying some powers of 2 and looking at the adjacent numbers and maybe look for a pattern, maybe find the answer already, who knows, right? Okay, so let's list out the powers of 2. Let's just list some out here. Okay, let's look at the adjacent numbers of these. Well, 1 and 3, that's not going to work. 3, that's not going to work. 7, that's not going to work. We have, whoops, we have 15 and 17. 17 is not going to work. 31 is not going to work. 63 and 65. Oh, look at that. Well, we just found the answer. 64 works as 2 to the n, so then n just equals 6. That's your answer. Yeah, that's your answer. Okay, so um, what's the takeaway from this problem? That you should try to in problems like this where it's pretty easy to apply what it's saying, you should just try some values and see if you like it helps you not only to like maybe look for a pattern to kind of solve it better, but also you might just like get the answer. And in this one, it seemed it was pretty likely for us to just like come across the answer, right? So yeah. Anything you want to say here, Bill?
I guess not. You're just trying out numbers. So, I mean, powers of two, those are really easy to test. So, those are really easy to test. And there's not really another way you can do this. Like, it's pretty hard to check for prime numbers unless you just check all of them. So,
Yeah, it's pretty hard to solve this problem systematically. So then it just gives you more reason to plug in more numbers, right? Yeah. Maybe don't go like too far, but I would say like at least to like 1024, right? And I mean, these are so easy to test, right? I mean, listing out the powers of 2 and just looking at the side-by-side numbers, and whether they are prime or not. So yeah, okay. Let's move on. Number 2, a sequence is defined by a sub 1 equals a sub 2 equals 1, and a sub n plus 2 equals a sub n plus 1 plus 2 times a sub n for n is greater than 0. What is the least value of k for which a sub k is greater than 1000? Okay, so our first number and our second number in our sequence are 1 and 1. And then this tells us that each next number will be the sum of the previous number plus 2 times the sum of the previous number before that. So this is kind of like a slightly different Fibonacci sequence. And we just want to find the least value of k for which the kth number there is greater than 1000. And what we should do here is we should just list down numbers until we get to 1000. So we should do that because sorry, this sequence grows pretty quickly. Like if you've ever seen the Fibonacci sequence, it grows pretty quickly. And this one grows even faster than the Fibonacci sequence, right? So definitely the best way and the fastest way to do this is just to list out the numbers until you get to 1,000. So let's just do that. So the third number will be 1 plus 2 times 1, which is 3, and then 3 plus 2 times 1, which is 5, and then 5 plus 6, which is 11, and then 11 plus 10, which is 21, and then 21 plus 22, which is 43, and then 43 plus 42, which is 85, and then 85 plus 86, which is 171, and then 171 plus 170 is 341, and then 341 plus 342 is 683, and then 683 plus 682 is 1365. And we see that this is the first one that reaches greater than 1,000. Okay, so that did not take us long at all. So now we can just count. This is the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th. So this is our k equals 12 number. So right, our answer is 12. Anything you want to say there, Bo?
This is just trying numbers. You just have to know that. You just have to see that, you know. This is a sequence that grows very quickly, so it'll be pretty easy to try numbers there.
Yep. 7 lines are drawn in the plane. There are 2 pairs of parallel lines, but not all 4 of these lines are parallel. The 3 other lines, which are not parallel to any of the first 4 lines, intersect at a single point, and there are no other points at which more than 2 lines intersect. Into how many regions do these 7 lines divide the plane? Okay. Maybe you can do this problem conceptually, like apply, like I don't even know, like just apply stuff. But you can also do this just by like drawing the figure and counting how many regions there are, right? And that's pretty easy, so we can just do that. So let's first draw the 3 lines that intersect at one point. Okay, and you need to make sure you draw your figure well, so that um, you get this problem right. Okay, so we have 4 other lines, and pairs of them are parallel, sorry, but not all 4 of them are parallel. And so we should draw that in our figure, right? And they can't be parallel to any other lines. So we need to be careful not to draw them looking like they're parallel to any of these lines that we've already drawn. Okay, well, we have no vertical lines, so we can just go ahead and draw those in. Now, we can't draw pairs of horizontal lines because that would look parallel with this one. So we should draw a kind of slanted horizontal line. So maybe it will look like this. And we have to be careful not to make any 3-line intersections because it says that the only one is this point and there are no others. Okay. And let's draw another one that is parallel to this one. Okay, that looks pretty good. And just remember that these 2 don't intersect and these 2 don't intersect either. Okay, so now we can just count how many regions we have here. Okay, well, we have 1 here, and if we extend this, we have 1 here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Oh, and 26. There we go. Okay. Yeah, and it's pretty effective to like count it by leaving a dot in each region. And then if you have any regions that don't have dots, then you'll know you'll need to count that one. Okay. So I counted 26 and yeah, that's your answer. Um yeah, anything you want to say there, Paul?
Mm, yeah, I mean, like, there's you can definitely like you said, you can definitely do this problem like algebraically. You can like there's probably you can probably calculate it, but there's so few lines. There's 7 lines, and this is not one of those graphs where like it's easy to mess up. Like as long as you get them all crossing the right way, you'll be fine. So I think
Yeah,
like on problems like this, you should definitely just draw it. There are questions where like the graph has to be absolutely perfect, but this isn't one of them. So
right. You're just counting regions, not at all like something very rigorous. And the constrictions that it gives, like you can't have like other like 3 lines intersecting. That's not this. Is very easy to avoid, right? So drawing a figure is definitely not bad here. Okay, let's move on. Number 4. Alec and Bu race to compete. Oh, sorry. Alec and Bu race to compute 1 plus 2 plus 3 all the way to n. Alec skips 2 numbers and gets a sum of 92. Bu double counts 2 numbers and gets a sum of 145. What is the value of n? Okay, so this is sum, right? And then Alec will skip 2 of these numbers, so essentially subtract 2 of these numbers from this sum, and he will get 92. And then B will double count 2 numbers, so essentially add 2 of these numbers into the sum, and we'll get 145, right? So it's pretty obvious that this sum will have to be in between 92 and 145, right? And we can just we have a formula for the sum, right? So we can just find we can just go ahead and find which few values of n will even be possible for that, and there shouldn't be a lot, and then we can just test for each value of n. Okay, so our sum of natural numbers to n formula is just um, n times n plus 1. That is a wacky 1 over 2. Okay, and it has to be in between 92 and 145. We can just test some values of n. Maybe test 10. Okay, that gives us 55, which is way too small. So let's try 16. Okay, 16 gives us 136. Okay, so let's try 17. And that gives us 153. Yeah, 153. And that's too big, right? Okay, 15 gives us 120, and 14 gives us 105. And 13 is going to be too small, but you can calculate it. And it's just 91. That's going to be too small. Okay, so we just have 16, 15, and 14 as values of n. We can just test any of these. We should probably go ahead and start with testing the middle because it's the middle, so it's, I don't know. Let's just test this one. Okay, so if we subtract 120 and 92, we get the value that Alec has to skip in total, which is 28. Let's think if this is possible. We have to have 2 numbers between 1 and 15 that will equal 28, right? So that he can subtract it. And this is possible, right? You can just have like 15 and 13. Okay. And 120 to 145 is 25. So he has to add a value of 25 with numbers that exist in there. And this is totally possible, right? You can have 15 and 10. Okay, so this works. So our n is 15. So yeah, that's the answer. So, I mean, we didn't test these. Um, but like, because the problem only has like one value of n, you just say this one, right? That's just, yeah. All right. Anything you want to say there, Bo?
Ooh. This problem did not really it's not really that hard. You just have to try the values. So there's not really much to say.
All right, let's move on. We're gonna need some space here. Okay. The dartboard is shaped like a regular hexagon. The six vertices are marked in blue, and the midpoints of the six edges are marked in red. When a dart is thrown and lands on the dartboard, the closest of the 12 colored points is located. The throw is said to be bluish if the closest point is blue. If the closest point is red, it is said to be reddish. If a dart is thrown and hits a random point in the dartboard, what is the probability that the throw is bluish? Express your answer as a common fraction. Yeah, and I think it gives us a hexagon here. Yeah. Okay. Oh wait, I can draw my own hexagons. So yeah. Um, the shape tool. Uh, polygon tool. Very cool. That's a bit too small. Oh yeah, there we go. Okay. Um. Okay, I'll just have it like this. Okay, so our bluish points will be the vertices. So these are blue, and our reddish points will be the midpoints of each of the edges. And you can label it all the way around. Um, and we want to find the probability, we land a dart and it's closest to a blue dot and not a red dot. So how are you going to do this? Well, um, like how do we find whether um a dot is going to be closer to this blue dot or to this red dot? Well, um, we can do this by drawing the line where all dots on that line is the same distance to both of these points, right? And then if a point is on either side of the line, then we'll know if it's closer to the blue or the red dot if we're just looking at these two, right? So basically, if we draw the perpendicular bisector to these 2 points, oh, that is so bad. Okay, let me try it. Yikes. I need a line tool. Uh, is it pen? Yes. That's so kind of bad. I'll just move it. Oh, what that? Oh, wait, what? Wait, what? Uh, oh, okay. That's kind of weird. Okay, yeah, if we have, that's so thin. What the heck? Okay, whatever. Okay, so if we have the perpendicular bisector to these 2 points, this blue and this red point, um, all the points on this perpendicular bisector are going to be equidistant from this point and that point, right? That's the property of the perpendicular bisector. So whatever side a point lands on like this line, then we'll know um whether it's closest to this blue point or this red point. Um, but we can't just consider these 2 points, right? If we only consider these 2 points, then it's saying that a point over here would be closest to this red point, right? So what we should do is we should essentially draw all of these perpendicular bisectors and look at those regions. So how am I going to do this? Let me see if I can copy this line. Yeah, I
Well,
got
you
it.
don't necessarily have to draw all of them.
Yeah, you don't have to draw all of
This
them
is
because it's
symmetrical in
symmetrical.
like a lot of ways. You can just find the area of like a single triangle and then just like it's the same for everything, same for all of them. So you can just find it in like a small
Well,
proportion.
you have to draw a few first. I only drew one.
Okay, yeah, it makes sense.
So,
You have to draw a few, but yeah.
okay. And those are gonna go like that. Okay. So, okay, I drew a few here. And if we look at this, it separates this into regions where if we have any dots in here, these will be closest to the blue point, right? And if we cross this line right here, it will be closer to the red point, right? Because we cross the perpendicular bisector of this point and this point, right? So then if we go into this region, this is all of this red's region, right? Not until we cross this line, which is the perpendicular bisector of these 2 points, and that will be blue. But if we draw the perpendicular bisector of this here and this, then it'll cross into another, or it'll cross it off into another region that looks like this, right? And if we draw all of them, we'll have like some sections like here. Um, and so what points would these be for? Well, these would be for the red points, right? Because the red points the red point here is definitely going to be closer to all of this than the blue points, which are farther, right? So all of this is just going to be red, right? Except for the little region right here, which is going to be for blue. Okay, so then we just need to calculate the area of this small blue region in comparison to the area of the entire hexagon, right? So let's just say the side of the hexagon is 1. We can do that because it doesn't specify at all, right? So if the side length of a hexagon is 1, then the area is just going to be 6 times 1 squared times root 3 over 4, right? Because we can divide the hexagon into 6 equilateral triangles, and they will all have side 1, right? And they will each have area side square times root 3 over 4, right? And we have 6 of them. Okay, so the area of our hexagon is going to be 3 root 3 over 2. Okay, now we just need to calculate the combined area of all these blue triangle things, or these kite things, and put it as a ratio to our hexagon area. Okay, well, what we can do is we can just find the area of one of these kites and multiply it by 6, right? But actually we can just, because this is symmetrical, we can just find one of these triangles and further multiply that by 2. Okay, so what is this? How do we get this? Well, we know that this side is 1, and we know that this is the midpoint, right? So this is going to be 1/2. But we also know that this line is the perpendicular bisector, right? So this has to be 1/4. Okay, and this is on the symmetrical line of the hexagon, right? So then it's going to be the angle bisector of this angle of the hexagon, and it is 120 degrees, right? So it's going to separate it into 60 degrees. So then we have, and this is a perpendicular bisector, right? So that this angle is 90 degrees. So then we have a 30, 60, 90 triangle. So because it's a 1/4, this side will be √3/4. Then we have the 2 legs of the triangle. So then the area will be 1/2 times √3/4 times 1/4. Okay, these 2 and 1/2 cancel. So then we have 3√3/8. Okay, so this is the area of all of our blue kites. So now the probability is just going to be 3√3/8 over the area of our hexagon, which is 3√3/2. So cancel out the 3√3s, then we just have 1/8 over 1/2, which is just what? Which is just 2 times, or 2/8, which is just 1/4. And yeah, that's our answer, 1/4. Anything you want to say there, Bill?
Mm, Okay, so for this problem, you actually didn't have to find the actual area of the things. Like, you could have noticed that if you were to
You mean
split,
make those triangle things?
yeah, you
Okay, sure.
the triangle itself could be split into more of the triangles. So you didn't have to find the actual area, and like if you notice that, that's probably faster than actually finding the area. So just
Okay,
something.
so what he's saying is that if we draw this line here, um,
Like you can just look at it on the scale of a like half of one of the equilateral triangles, because all of the things are on that, like
um,
half of one of
okay,
the equilateral triangles.
he's saying that if you draw like one of these equilateral triangles, then you can see that the equilateral triangle will be composed of like
You can
8 of these small
Yeah, you can
triangles,
split it up. And it's pretty obvious you can split it up because they all,
like
they
like
all share the
this.
same base and same height. So it's pretty obvious
Yeah.
that you can split it up this way.
So like you can split this up because this is like the midpoint and all of them are perpendicular bisectors, right? And and yeah, and they're all going to be similar, so and they all share a side length. So yeah, you can just separate it like that. And and all the equilateral triangles are going to be the same, right? So you really only have to look at the blue in here compared to the triangle, right? And if you look at this, there are 8 of these triangles in the equilateral triangle, and there are 2 of them that are blue. So then that's just 1/4. I don't know, maybe that's a little bit faster, but I mean, solving for the area is not bad at all either. So, all right, let's move on. Number 7. The numbers 1, 2, 3, all the way to 15 must be arranged in the circles of the figure shown with one number per circle and each number used exactly once, in such a way that each arrow points from a smaller number to a larger number. How many such arrangements are possible? Okay, so we're putting the natural numbers 1 through 15 into all these circles, and um, one circle per number only used once, and each circle points from a smaller number to a larger number. And we want to find the total number of possible arrangements. Okay, so it should be pretty obvious that the largest number 15 has to be in the top circle, right? Um, basically, um, this circle will have to be greater than all the other circles, right? So obviously they're greater than these two circles, but these two circles are greater than these two circles, and these circles are greater than all of these circles, right? So this one has to be greater than all of the circles. So this number has to be 15. Then how should we do it? Okay. Well, what we can do um is now we have 14 numbers left, and we can choose 7 of these numbers. We can choose 7 of these numbers. Um, we can choose 7 of these numbers to go into this branch, and the other 7 to go into this branch. And we can do this because whatever 7 numbers we choose in this branch, it will always have the same number of permutations. And that's because whatever numbers you choose, they're always going to form a sequence where it's getting smaller and then getting larger. So the actual value of the numbers don't actually matter, right? It just matters like um how it works with which is smaller and which is larger than the others. But whatever 7 numbers you choose, they're always going to have the same thing, right? Like 1 is the smallest, 1 is the second smallest, 1 is the third smallest. It's always going to have that, and that's all we really care about. So whatever 7 numbers we choose, it's going to be the same thing. So we can start with this 14 choose 7, and then multiply it by the number of permutations that we have in this tree, right? But if we choose 7 numbers and we look at this tree now, the largest number again has to be in that top bubble, right? So if we have it there, well, actually, so this 14 choose 7, um, we're gonna have to multiply this by the square of the permutations of one of these branches, right? Because we choose this, and then we have the 2 branches, and we need to multiply it by the permutations of this branch and by the permutations of this branch, right? Um, and the permutations are going to be the same. So then it's just like squaring the permutations of one branch. So we're gonna have 14 choose 7, and we're gonna find the permutations of this branch, and we're gonna have to multiply by 14 choose 7 square, right? Okay, I hope that makes sense. So yeah, I don't know. Well, sure, we can just call it x for now. So we make sure we have to square it. So the permutations of this branch is x. Okay, so we have some 7 numbers, and again, the largest number has to be in that bubble. And we can apply the same thing to this tree with the larger tree that we did to find the permutations of this tree, right? We can do 6 choose 3, and we're going to multiply it by the number of permutations of one of these smaller trees squared, right? And then how many permutations do we have in the smallest tree? Well, it's just 3, right? Because the largest has to go there. And then you can arrange the other 2 however you want. Oh, wait, did I say 3? I meant 2. Sorry. Okay, and we have to square that, right? So this is the number of permutations we have of this tree. And we had to square that, right? And then multiply it by 14 choose 7. Now we just need to figure out what this is. And if you calculate it, you will get a pretty large number. You will get 2196480. Honestly, that doesn't look like it's going to be the answer for this one, especially since you have such a small blank. But yeah, it's actually the answer.
Yes, the judgment of whether a question answer is right or not is how big the blank is.
Yes, of course. Um, okay. There are probably other ways to solve this. Um, but this way is pretty good, I would say. Um, Definitely better than like looking at casework. I mean, that would be so bad. Anything you want to say here, Bill?
Right, like Austin said, definitely better than casework. We tried casework and it did not work out. Um, so I mean, for this problem, it's more of just like the concept of if you choose a bunch of like in this case, if you choose a bunch of
Yeah,
numbers.
the concept of if you choose a set of numbers, they're going to have the same number of permutations as if you choose any other set of numbers.
Yeah, and like also if you choose a set of numbers, yeah, okay, like basically what Austin said, that's what I meant. Just like they will
Yeah,
have, there's only like there's a set number of ways you can order them if you choose a number,
right,
a set of
right.
numbers.
So then you could just multiply the number of ways um, that you can choose that by the number of permutations that you'll have in there. That's pretty important. And this actually showed up in like one of our past problems, if I remember correctly. So yeah, I guess it is pretty important. I haven't seen this too much in like AMC or Amy though, but whatever. All right. Okay, last one in team. No, actually, I'm done. There are 10. Never mind. We have three more. Okay. Number 8. There's just one positive number x such that 3x plus 5, 4x plus 4, and 5x are the side lengths of a right triangle. What is this value of x? Express your answer as a common fraction. So if these three are the lengths of a right triangle, then they have to be satisfying Pythag, right? But the problem is we don't know which one is the hypotenuse. But what we can do is go ahead and just set up three equations for them, and then see which ones work, right? So just set up three equations into your calculator of each one of these being the hypotenuse. Now I've already done this. And if you do, only one of them works. Only the one with 3x plus 5 as hypotenuse works, with equaling a positive number. And when you do that, you just get x equals 1/2. Um, and that's it. This problem is really easy. You just make three equations and see which one gives you a positive value of x. Yeah, Lishan? Yeah. Yep. You just make formulas and solve them. You could do it by hand, but that's really not necessary. You have calculators on team, so just if you have a TI, just make a quadratic equation and use the solve function. Yeah, no problem. Anything you want to say here, Bill?
Oh, nah, this was fairly easy, I think.
Yeah, this is really easy. There's like 4 times as many people that solved this than number 7 or something like that. Yep. All right, number 9. How many sequences of integers a, b, c, d, e exist such that a is greater than or equal to b, is greater than or equal to c, and so on? And a squared is less than or equal to b squared, is less than to equal to c squared, and so on, all the way to less than or equal to 5. Okay, well, the first thing that we can notice is that all of these integers squared have to be less than or equal to 5. Which means what? Which means that all of the integers a, b, c, d, e have to be in the set of -2, -1, 0, 1, and 2, right? Because these are the only integers squared that are less than or equal to 5. Any other integer, it will be too big. So what? Our answer is 1, right? We just we have 5 numbers. We have 5 numbers, so we only have one thing, and these work in that, right? No. You have to be careful on that. The answer is not 1. And that's because it did not say anything about A, B, C, D, and E being distinct. So, we could have all of them being -2 or all of them being 0, and that would be way different cases. So, be careful on that. The answer is not just 1. So, with A, B, C, D, and E being not distinct, this problem is a lot harder. Um, yeah. So we're gonna have to do some sort of casework to dissect this more. Um, yeah, we're gonna have to do something here. So we can try just casework with integer a, and seeing or testing values of a. So we can have all these cases: a equals 2, a equals 1, a equals 0, a equals -1, and a equals -2. All right. So what is going to happen when a equals 2? Well, let's look at this equation. A equals 2, 2 is the biggest in our set. So it's always going to be bigger than all of these, right? So with that, there's no constraint on B through E, except that B still has to be greater than or equal to C, which has to be greater than or equal to D, and so on, right? Okay. And now let's look at this one. A squared in this case is going to be 4. And all these B squares, C squares, D squared, D squared, and E squared have to be greater than or equal to A squared, right? Which is 4. So how is that going to happen? The only way that's going to happen is if B through E are -2 or 2, right? Because -1 through 1 gives a smaller square than 4, right? So B through E, when A equals 2, can only be -2 or 2, and we still have to satisfy that, right? Okay. But if they are -2 or 2, then we don't have to worry about this at all, right? Because then they will all be 4 and they're all equal to each other. So we don't have to care about that anymore. We just have to care about that. So then how can we arrange it? Well, if we have any -2s, they have to be at the very end, right? Because they're smaller than the 2s, right? So then what cases can we have? Well, we can have them all being 2s. We can have the last one being -2, or both, or the last two being -2, or so on, right? So how many cases is that? That's going to be one of this, and then 2, 3, 4, 5, right? So that's going to be 5 cases. And let me know if you ever want me to explain anything more. There's going to be I don't know, this stuff is going to be kind of iffy. So yeah, just let me know if you want me to repeat something or something. Yeah. Okay. So that's all our cases for a equals 2. So yeah, it's just 5. Okay. Now let's look at a equals 1. Let's look at the squares first. So 1 squared is going to be 1, and all the other squares have to be greater than or equal to 1. So this means that b through e can't be 0, right? Because that squared is going to be less than 1, which we don't want. So just from the squares, b through e can be 2, 1, -1, or -2. And if they are any of them, we don't have to worry about the squares at all, right? Because Oh, no, never mind. We actually do have to worry about the squares, yeah. So we have to worry about the squares in that if we have 2 or -2, they have to be at the end because then squared is 4, while the 1 and -1 squared is 1. So they have to be at the end here, being greater than being greater than the ones. So if we ever have 2 or -2, they have to be to the right. And if we ever have 1 or -1, they have to be at the left. Okay. Now let's look at this one. So A is right here, and it has to be greater than or equal to everything, right? So that is saying that B through E can't be 2, right? Okay, but then they can be 1, -1, or -2, and that would still be satisfied. Okay. So then, with the square thing, we only have to think of that if we have any -2s, they have to be at the end because them squared are 4 and they're going to be greater than or equal to, or they're going to be greater than the 1 squared. Okay. Okay. So, let me write this somewhere else because it's going to take up some space. So let's start with the base case of 1, 1, 1, 1, 1. This definitely works, and it gives us one case. Um, Now let's try. Okay, this last digit can be -1 or -2. Let's just look at the case where it's -1 first. Whoops. Okay, let's just look at the case where it's -1 first. None of these can be -2, right? Because again, if we have any -2s, they have to be at the end. Um, And so this -1 is at the end, which means none of these can be -2. So if this is -1, then these can just be 1 or -1. And it's like our 2 and -2 case, right? So we're going to have one case where it's 1, 1, 1, 1, and then -1. And then we're going to have another case where the second to last one is -1, and another where this one is -1, and another where this is -1, right? So how many cases is that? That's 4 from this being -1. Well, now let's look at if it's -2, right? Then the second to last number can be -1 or -2 now, because now we have a -2 at the end. This one can still be -2 and still satisfy the square thing. So we're gonna have one case from the base case right here. Now we can do casework on this one being -1 or -2. So when it's -1, it's going to be the same thing as this one, right? But in this case, we're only going to have 3 cases here. So that's going to be 3. Now let's look at this -2. Um, if this is -2, then we can have this one being -1 or -2, right? Okay, but don't forget to write this base case down. That's going to be 1. And then we're going to have to deal with this -1, and it's like the same as the other -1s. But we're only going to have 2 here. And now if this is -2, then this 1 can be either 1, -1, or -2, right? So then that's 3. And we don't have to look at this 1 at all because we're just looking at the A = 1 case, right? Okay, so that's all of our cases for this. So now we just sum this up. We have a 6 and 4 there, so that's 10. And then we have 5. So this is 15. So our A = 1 case is 15. Now let's look at A = 0. Okay, with A = 0, let's look at this equation first. This is going to restrict B through E having to be -1 or -2 or 0, right? If they are 1 and 2, then they cannot be smaller than or equal to 0. And the squares are saying that the -1 and -2s have to be at the end, right? Just by the same reasoning as before. Now, the thing about this one is that it's actually like the exact same case as our a equals 1 case. So what happened in our a equals 1 case, right? In our a equals 1 case, we had the three numbers 1, -1, and -2. And our constraints were that -1 and -2 have to appear um in here just based on that, right? And now we have in 0, we have the case of 0, -1, and -2. But this is the same case, right? Because -1 and -2 still have to follow the same thing. It doesn't matter whether this is 1 or 0. And the squares thing still stays the same because the zeros will always be at the left just from that, right? The zeros must always be at the left just from this. And from that, the squares are already fulfilled for 0, right? Because the squares of 0 are always going to be less than or equal to that, right? So this case will be the same case as what we did in 1, -1, and -2. So then we can just skip that and use the same number as we got for a equals 1, which is 15. Now let's look at a equals -1. With this one, we can only have b through e being -2, right? And if they are -2, then they have to be at the end, right? And if we look at our squares, it's saying the same thing, right? If we have any -2s, they have to be at the end here. Okay, so then what? Then we can just do -1, -1, -1, -1, -1. That's our base case. And we can just switch all of these to -2, right? And they would all work. So how many cases then? Well, we have the base is 1, and then switch 1 is, that's another, and then this is another, so that's 3, that's 4, that's 5, right? So that's just 5 cases there. Okay, and a equals -2. Well, just from looking at this thing, b through e can only be -2, right? And all of them being -2 also satisfies this. So then we just have one case of -2, -2, -2, -2, and -2. Okay, so now we just need to add up these cases. It's just 41. And that is our answer, 41. All right. Anything you want to say there, Bill?
That was one heck of a problem. Uh,
It's like 15 minutes, I think.
yeah, that's pretty long, 15 minutes. Uh, I guess not really. I mean, it's just really like, uh, I completely, blank. It's just tedious, I guess. You just have to find these stuff.
Yeah. And there's not really a great way to do this. Mm, or casework is at least the most straightforward way. Maybe there's something else that's whack. Um, and maybe it's better, but that's kind of hard to find, I feel like. All right. Any questions for this poem? Well, we're nearing the end here, so if you have any questions, we can discuss that. Okay. Well, let's move on to the last one. Okay. In the city of Trichotomy, every day the weather is exactly one of the following: sunny, cloudy, or rainy. Each day has a 50% chance of being the same weather as the day before, and a 25% chance of having each of the other two types of weather. If it does not rain on Friday, what is the probability that there will be no rain on the weekend, Saturday and Sunday, especially in certain as a common fraction? Okay, so on Friday it is not raining. Okay, so it's either sunny or cloudy. And for the chance that it goes to rainy on Saturday is 1/4, right? Because it's a 25% chance of having each of the other two types of weather. So the chance that it is not rainy on Saturday is 3/4, right? And Saturday, if it's not raining, it's going to be sunny or cloudy, right? So same thing, Sunday, it's also 3/4. So just 3/4 times 3/4, just 9/16. And that's your answer. Um, this problem is pretty funny, considering the last problem. Yeah, this one was extremely easy. Um, yeah. Uh, so that's the end of 2015 national team. That's it for 2015 nationals. Um, yeah, this is a nationals problem too. I don't know. But yeah. So this is all we have for today. But we still have 10 minutes left. If you have any like other random questions you want us to do, we can also try that. Uh, we can we're gonna move on to 2016 nationals um for next week. Unless you're like I've already done 2016 nationals, then we can do different years nationals. Oh wait, no. No, we've already done 2016, right? No, I'm done. Yeah, I think we've already done 2016. So we'll move on to 2014 actually. Hold on, let me look at this. Yeah, I'm pretty sure we've done 2016. Okay, yeah, we'll do 2014 next week. 2014 Nationals. Um, yep. All right. Um, okay. I don't know. Is there anything you want us to do? Maybe we can just do a random AMC problem. Should we do that?
All right. Yeah.
Oh, let's go.
All right.
How about last year's last year's 12B, the last problem of last year's 12B,
All right. That I am gonna
number
fail at
25.
this. I swear.
Let's go in 10 minutes.
I'm gonna fail at this.